electric current and circuit. In our day-to-day activity, electricity has become an important part of our life, without which we are unable to use the modern gadgets and devices. In order to make these devices work, electricity is required to flow through them. The basic of all electrical phenomena is electric charges. We know that all substances are made up of atoms. An atom consists of a positively charged nucleus that is surrounded by negatively charged particles called electrons. However, the electrons are weakly bound to the atom and can be removed from or added to an atom. Charge on an electron is denoted by a symbol E-, and that on a proton is E+. And the SI unit of electric charge is coulomb, named after the French physicist Charles-Augustin de Coulomb. Charge on an electron is minus 1.6 into 10 to the power minus 19 coulombs, and the charge on a proton is plus 1.6 into 10 to the power minus 19 coulombs. Total charge of an isolated system remains constant. The electric charge can neither be created nor be destroyed. This property of charges is called law of conservation of charge. Total charge on a body can be obtained as the product of the number of free electrons or protons and the charge on an electron or a proton. This expression shows that 6.25 into 10 to the power 18 electrons constitute a charge of 1 coulomb. Like mass, charges also have additive property, according to which the total electric charge on an object is equal to the algebraic sum of the charges distributed on the different parts of the object, where Q1, Q2, Q3 and so on are the electric charges on different parts of the object. Though the total mass of an object always remains positive, that is, mass cannot be negative or zero, but the net charge on the object can be negative or positive or neutral. It is very easy to remove the electrons from an atom, whereas the protons are practically impossible to be removed out from the atom or from the nucleus. Also, the energy required to remove an electron from the atom depends how tightly it is bound to the atom. Based on this understanding, all matter around us can be categorized as conductors and insulators. The material that does not allow the passage of electrons through it is called a poor conductor of electricity or an insulator. For example, paper, dry wood, pure water, plastics, dry cotton, etc. And the material that allows the passage of electrons through it is called conductor of electricity. For example, metals, impure water, living matter, etc. Good conductor of electricity can be charged by bringing it in contact with another charged object. A very good example of charging objects by this method is an electroscope. Let's see an electroscope. It consists of a metal disc connected to a conducting rod. The lower end of the charging rod is connected to a pair of thin gold leaves. The whole setup is in a glass jar. When a positively charged comb is brought and is made to touch the metal disc, the gold leaves diverge, indicating the presence of the like charges on them. In this method, charge is transferred from the comb to the metal disc and then to the gold leaves. Here, both the leaves acquire the positive charge. This method of charging is referred to as charging by conduction. When an object is rubbed with the surface of another, some electrons get transferred from one body to another. The body that gains electrons becomes negatively charged and the one that loses electrons becomes positively charged. This process of charging is called charging by friction. As here, a rubber balloon is rubbed with a woolen garment and becomes positively charged. The woolen garment is left with a negative charge because some electrons are transferred from the balloon to the woolen garment. Electrically charged bodies may repel or attract each other. For example, let's take one more positively charged balloon. When the two positively charged balloons are brought close to each other, they repel each other. This shows that the two similar charged objects always repel each other. Let's take another rubber balloon and rub it with a silk garment. Now, the balloon becomes negatively charged and the silk garment becomes positively charged because some electrons are transferred from the silk to the balloon. When this negatively charged balloon is brought close to the positively charged balloon, they attract each other. This shows that two objects with opposite charge always attract each other. The very basic nature of the two types of charges is that two like charges repel each other, while two unlike charges attract each other. On the basis of the properties of charges, one can charge the other conductor. Let's see how. When a positively charged comb is brought near the metal disc, the gold leaves diverge. That again shows the charging of the two leaves. In this method, charge is not transferred from the comb to the metal disc, but the electrons of the conducting rod attract towards the comb. This way, the metal disc gains the electrons and thereby acquires a negative charge. On the other hand, the gold leaves have the deficiency of the electrons. That is, both the leaves acquire positive charge. This method of charging is referred to as charging by induction. The most common natural phenomenon related to charges is the thunderbolts of lightning across the sky during the rains. Clouds in the lower region of the atmosphere get negatively charged as they are blown by wind. When a heavily charged cloud comes close to any other object like ground or a building, there may be a strong spark of lightning. As a result, huge amount of negative charges jump to the oppositely charged ground or the building. On the other hand, clouds in the upper region get positive charge. When a heavily charged cloud comes close to another cloud, there may be a strong spark of lightning as a huge amount of negative charges jump to the oppositely charged cloud. In both the cases, lightning is due to the strong attractive force between opposite charges. As a safety measure, tall buildings are installed with lightning conductors. These are long and thick metal rods whose split upper ends are sharp, pointed, and the lower end is attached to a large metal plate buried deep under the earth. When lightning strikes a building having a lightning conductor, the flow of charges is quickly carried to the lower end of the conductor under the earth and is distributed to the immediate surroundings. Do you know that the passengers on ships, especially on oil tankers, are provided with metal-plated shoes? When a person walks on the deck of a ship, the soles of his shoes develop a charge on them due to friction. As he walks, an opposite charge is induced on the deck, and sparks appear as a result of two opposite charges in contact with each other. To avoid this condition, the soles of shoes to be used on the decks are provided with a metal plate under them, so that the charge does not accumulate on the soles but easily flows out. Charged particles that flow in a definite direction through a conductor constitute the electric current. The electric current occurs naturally in many situations, such as the case of lightning. Charges flow from the clouds to the earth through the atmosphere, causing an electric current called transient current. The transient current ceases when the flow of the charges stops. In general, rate of flow of charge passing through a given point in a conductor is called electric current. If charge Q passes through a fixed point of the conductor in time t, then the magnitude of the current flowing through the conductor is the ratio of the charge and time. Its SI unit is ampere, named after French physicist André-Marie Ampère. 1 ampere of current can be defined as when 1 coulomb of charge passes through a cross-section of a conductor in 1 second, the current passes through it is called 1 ampere. As a matter of convention, the direction of flow of positive charge gives the direction of current. This is called conventional current. While the direction of flow of electrons gives the direction of electronic current, the direction of electronic current is opposite to the direction of conventional current. Let's try a numerical problem. Calculate the current in a wire if 900 coulombs of charge passes through it in 6 minutes. Using the relation for current and charge, it comes out to be 2.5 amperes. An electrical circuit is a closed loop in which current flows. It is the interconnection of electrical components such as a cell or a battery that is a source of electrical energy. Electrical appliances such as an electric bulb and electric heater, also called load, are connected to various components with the help of connecting wires that are made up of insulated copper wire. A key or a switch is used as circuit breaker. However, conventional symbols or pictograms are used to represent an electric circuit. For example, a cell is represented by two unequal parallel lines, in which the larger line represents a positive terminal and the smaller one represents a negative terminal of the cell. These two lines are not joined together. In a battery, a number of cells connected in series are used. Therefore, a battery is represented by a series of the symbol of cell. To represent an open circuit, an open key is used that is represented by a discontinuous line where two small circles are used to show the junction points. However, a continuous line represents a closed circuit. A fixed resistance is represented by a zigzag line and multiple resistances may be joined in series or parallel. A rheostat is used as a variable resistance. It is represented by a zigzag line along with an arrow. Electrical appliances are represented by a coil-shaped symbol. To measure the amount of electric current flowing through the circuit, an ammeter represented by encircled A is used. And to measure the potential difference in the circuit or across any particular device, a voltmeter represented by encircled B is used. Sometimes another similar device, that is a galvanometer, represented by encircled arrow, is also used. It not only detects the presence of current, but also indicates the direction of current. Main supply of an alternating current is represented by encircled wave sign. To prevent a circuit or costly devices from overheating and short-circuiting, a fuse is used. It prevents the circuit by melting and thereby breaking the supply of current. In an open loop, a circuit shows no flow of current, but in a closed loop or with a closed switch, it shows flow of current. When two or more bulbs are connected in a simple circuit, it is called a series combination. On the other hand, when two or more bulbs are connected completely in parallel circuit, it is called a parallel combination. Series and parallel combination of resistors. According to the Joule's law of heating, electric work done by the charge carriers moving in a conductor produces heat. And the amount of heat produced by a conductor can be measured by using the relation established by Joule. If a conductor having resistance R carrying current I for time t, then the heat energy produced by it is I square R into T joule. In terms of calories, it becomes I square R into T upon 4.18 calories. In your previous class, you have studied that mechanical power is the rate of doing work, or it can be defined as the amount of work done or energy consumed per unit time. In electric circuit, the rate at which the electric work is done by the source in maintaining the current is called electric power of the circuit. In other words, it is the rate at which the electrical energy is supplied by the source in maintaining the current is called electric power of the circuit. Like mechanical power, it is also represented by symbol P, and its SI unit is joule per second or watt, named after the British engineer James Watt, who developed the concept of power. If a current I ampere flows through a conductor of resistance R ohm for a time T second under a potential difference of V volt, then electric work done to maintain the current is given by W equals VI T joules. Thereby, electric power is equal to the product of potential difference across the conductor and the current flowing through the conductor. Since the SI unit of potential difference is volt and that of electric current is ampere, therefore, SI unit of power also becomes volt ampere. The unit of power, that is watt, can be defined as the power of an electric circuit is said to be 1 watt if 1 ampere current flows in it against a potential difference of 1 volt. Other units of power are kilowatt, megawatt, where 1 kilowatt is equal to 1000 watts and 1 megawatt is equal to 1 million watts. However, commercially unit of power, especially mechanical power, is horsepower, where 1 horsepower is equal to 746 watts. By using the Ohm's law, expression for electric power consumed by a conductor can be modified as shown. The source of power is an external source to keep a steady current through a conductor. In a simple circuit, where the current is supplied to a conductor by the cells, it is the chemical energy of the cells which supplies the power for as long as it can. The total electric work done in maintaining the current in an electric circuit for a given time is called electric energy consumed in the circuit. To accomplish electric work, energy is supplied from a cell or a battery. Since electric work done is VIT joules, thereby electric energy consumed in a circuit is also equal to VIT joules, that is, the product of potential difference, current and the time. This can be measured as the product of electric power and the time. By using the formulae used to measure electric power, the formulae to measure electric power can be obtained as shown. In general, SI unit of electric energy is joule, but in terms of watt, it is watt-second. 1 joule can be defined as 1 watt into 1 second. Further, the commercial unit of electric energy is called kilowatt-hour. Thus, it can also be said that 1 kilowatt-hour is the total electric energy consumed when an electrical appliance of power 1 kilowatt works for 1 hour. 1 kilowatt-hour is also equal to 1000 watt-hours. This is equal to 1000 watts into 3600 seconds or 3.6 into 10 to the power 6 joules. It should be noticed that the number of units of electricity consumed is equal to number of kilowatt hours or is equal to product of watts and number of hours divided by 1000. Let's now understand the energy consumption made by electrical devices in a domestic setup, and the commercial unit of electric energy is kilowatt-hour. Let's see a problem. An electric bulb is connected to a 220-volt generator. The current is 0.50 ampere. What is the power of the bulb? Using the expression for power, it comes out to be 110 watt. In next problem, an electric refrigerator rated 400 watt operates 8 hours per day. What is the cost of the energy to operate it for 30 days at rupees 3 per kilowatt hour? The total energy consumed by the refrigerator in 30 days would be 96 kilowatt hours. Therefore, the cost of energy to operate the refrigerator for 30 days comes out to be rupees 288. In next problem, an electric lamp of resistance 200 ohms is connected to a supply of 250 volt. If the price of electric energy is rupees 1.20 per unit, find out the cost of lighting the lamp for 30 hours. Consumption of electric energy by the lamp in 1 hour comes out to be 0.3125 units. Hence, the cost of electric energy for lighting the lamp at the rate of rupees 1 and 20 paise per unit for 30 hours comes out to be rupees 11 and 25 paise. In the next problem, an electric lamp of rating 40 watt 250 volt is used for 5 hours daily. If the price of electric energy is rupees 1 and 20 paise per unit, find out the cost of lighting the lamp for 30 days. Consumption of electric energy by the lamp in 5 hours comes out to be 0.2 units. Hence, the cost of electric energy for lighting the lamp at the rate of rupees 1.20 per unit for 30 days comes out to be rupees 7.20. 100 joule of heat is produced each second in a 4 ohm resistance. Let's find the potential difference across the resistor. current through the resistor can be measured as the square root of the ratio of heat energy with the product of resistance and the time, and it comes out to be 5 amperes. Thereby, the potential difference across the resistance comes out to be 20 volts. Suppose a family uses a television of 110 watts for 2 hours per day, a 100-watt bulb for 10 hours every day, a fan of 200 watts for 6 hours a day, and an air conditioner of 2 kilowatt for 8 hours a day in their home. The total consumption of electrical energy in a day can be found out by multiplying the wattage of the unit by the number of hours of its usage and add them up. So for the television, it is 0.22 kilowatt hour. For the bulb, it is 1.0 kilowatt hour. For the fan, it is 0.12 kilowatt hour. And for the air conditioner, it is 16 kilowatt hour. Thus, the total units consumed per day are 17.32 kilowatt hours or 17.32 units. Now, if the cost of electrical unit is 2.5 rupees per unit, then the cost of electrical energy consumed per day is the product of 17.32 and 2.5 to get 43.30 rupees. So the cost of electricity for this family for a month of 30 days will be 1,299 rupees. Let us see one more combination of resistors, which is the mixed combination of resistors. In the mixed combination of resistors, some resistors are combined in series and some in parallel. Here, the resistors R1, R2 and R3 are connected in series between the terminals A and B, having their equivalent resistance as Rs, while the resistors R4, R5 and R6 are connected in parallel between the terminals B and C, and their equivalent resistance is Rp. The equivalent resistance for series combination Rs is the sum of the resistors R1, R2 and R3. For the equivalent resistance for parallel combination, reciprocal of Rp is the sum of the reciprocal of resistors R4, R5 and R6. On simplification, we get the simplified value of equivalent resistance as shown. Let us see some advantages of mixed combination of resistors. If there are more than 2 bulbs, then some can be connected in series and others in parallel. This circuit is neither simple series nor simple parallel. Rather, it is a combination of series and parallel circuits. In this case, if the filament of any one bulb is broken, then current will still flow through the other branch. Hence, the bulb in the same branch would not light up, but the bulbs in the other branch would. Let us have a look at another combination in which 2 bulbs A and B are in series and bulb C is connected in parallel to B. If the filament of the bulb C is broken, the bulbs A and B would continue to light up, but the brightness would decrease because it becomes a simple series circuit, and hence the effective resistance of the circuit increases. On the other hand, if the filament of the bulb A is broken, then the bulbs B and C both would not light up at all.